एस्कॉर्ट वॉलंटियर्स, प्लीज आप अपने स्टूडेंट्स को बैठने के लिए बोल दें। देर आर एस्कॉर्ट वॉलंटियर्स, प्लीज आप अपने स्टूडेंट्स को बैठने के लिए बोल दें। देर आर
Purity. Are you the person coordinating this?
Yes, we are all. Yes.
You are there, right?
Yes.
So there are people to introduce people.
On now. You can get.
एस्कॉर्ट वॉलंटियर्स, प्लीज आप अपने स्टूडेंट्स को बैठने के लिए बोल दें। देर आर प्लीज सेटल डाउन। आप वहां बैठ जाइए, वहां पे जगह है काफी। सॉरी, प्लीज डोंट कीप योर बैग्स ऑन चेयर्स। बैग्स हटा ले चेयर से प्लीज। आप नीचे भी बैठ सकते हो अगर जगह नहीं मिलती तो, देयर इज नो प्रॉब्लम इन दैट, पर प्लीज सेटल डाउन। आगे आ जाओ, आप लोग नीचे बैठ सकते हो, यहां पे जगह है। यस, आप ऐसे इधर थोड़ा डिस्ट्रीब्यूट होके बैठ जाओ, यहां आपको बस स्क्रीन दिखनी चाहिए। आप सबको स्क्रीन तो दिख रही है ना वहां पे? ओके, गुड। आप ऐसे दो की लाइन बना के वहां पे बैठ सकते हो। आप थोड़ा शिफ्ट हो जाओ ताकि एक और लाइन बैठ सके। प्लीज कम फॉरवर्ड, यू कैन सिट फ्रॉम हियर सो दैट मोर पीपल कैन अकोमोडेट। आप आगे से बैठना शुरू करो ताकि पीछे से आने वालों के लिए आसानी रहे। ओके, आई स्टिल सी पीपल स्टैंडिंग, जगह नहीं है। खड़े रहना मुश्किल रहेगा, सेशन लंबा है, सो प्लीज फाइंड स्पेसेस। सम पीपल कैन कम हियर, अ फ्यू लाइक 3 or 4. निपुण, इनको इधर में। हाँ, दो तीन यहाँ आ सकते हैं, दो तीन वहां। आज अपने दोस्तों के साथ ना बैठो, चलेगा, इधर आ जाओ। टॉक है बहुत अच्छे अच्छे, इधर आके बैठ जाओ, दो तीन यहाँ पे आ सकते हो। यू हैव टू सी द स्क्रीन। स्क्रीन विजिबल है? पीपल, स्क्रीन विजिबल है? ओके, आप यहाँ पे आके बैठ सकते हो, आगे थोड़ा सा, थोड़ा आगे। आप जो बैग्स चेयर के साइड में मत रखो, आगे रखो, ताकि जो नीचे बैठ रहे हैं उनको जगह मिले। ओके, हेलो, एम आई ऑडिबल? ऑल सेटल? शैल वी स्टार्ट? इतनी लो एनर्जी में टीआईएफआर के अच्छा नहीं लग रहा क्या? लग रहा है एक दो को लगा बस अभी तक। हाउस द जोश? इट्स ओके, यू कैन कॉल मी सर, नो प्रॉब्लम। ओके, सो वेलकम टू टीआईएफआर। आप अभी यहाँ पे बैठे हो, यू आर गोइंग, एवरीवन इज कंफर्टेबल विथ इंग्लिश एंड हिंदी, क्योंकि उसमें स्विच होगा। ओके, सो मैं आपका बहुत समय नहीं लूंगी। इसके बाद से आपके लिए बहुत इंटरेस्टिंग टॉक्स, और टॉक के बीच में बहुत अच्छे क्वेश्चंस, क्विज, और उनके लिए हैं रिवॉर्ड्स। तो आपको टॉक को अच्छे से सुनना है, क्या पता उसके क्वेश्चंस क्विज में हो, और रिवॉर्ड्स तो और भी अच्छे हैं। सो यू हैव टू बी अटेंटिव, यू हैव टू बी अटेंटिव कि टॉक के एंड में आप क्वेश्चंस भी पूछो, ताकि हो सकता है कि आपके क्वेश्चंस भी हमारे क्विज में हो। सो डीले किए बिना हम शुरू करते हैं। पहले स्पीकर को बुलाते हैं, डॉक्टर शुभदीप मुखर्जी, एंड ही इज गोइंग टू टॉक अबाउट यूनिवर्स की कहानी, ग्रेविटेशनल वेव्स की जुबानी। वेलकम डॉक्टर शुभदीप मुखर्जी।
Hello everyone, do you hear me well? Do you hear me well? Good. So welcome to TIFI, National Science Celebration. I am going to start with one particular topic in science, which is on astronomy and astrophysics. So how many of you are astronomers? How many of you have seen the stars on the sky and tried to understand what is there? I have done as a child. Did you? Then all of you as astronomers, because we try to look on the sky and understand what's really going on there. What are those little twinkle dots? No? What we have learned in the frontier of universe. What is something which we can see and something which we cannot see by our eyes, and combining all those, how we can understand what is there in the universe, in those black dots, just always twinkling on the sky. So all of this have each other, depending upon whether in Mumbai or some other place, sky may be a little more darker or not. See these stars. No? It's really there. You can see. Do you think that there's all the stars we have so far? There's the only number of stars you can see, and that's all in our universe? Great. So, if at least person like me has a much better eye, possibly something like this. When you take a big telescope, which can see even faintest light from these stars, which are in the galaxies, which are very, very, very far away, sky looks beautiful. Sky looks amazing. It's all over the place. It's maybe very difficult to see a spot where there is not a star. Correct? So it's very fascinating, I mean, at least as a kid, it's very fascinating to see that the stars, little lights are coming to us, that in some distance, lights are falling from this very distant galaxies to us. Correct? See it. Do you agree? However, whether there is anything else, any other kind of waves which is coming and falling on us? Any guess? Anyone? Loudly. Even if you are wrong, don't worry. I hear someone is saying something, but I can't make it out. But the question that scientists ask to ask is, well, are there something else? From those distant galaxies having stars, is the only thing we can measure is electromagnetic waves or there's other kind of waves or other kind of messengers which are coming from those distant objects to us. And if we can detect them, need not be by which we can build based on the physics understood from our lab. And gravitational waves is one such particular signal. So the stars in the galaxies that you see, from those galaxies, if there are some objects, I'll tell you what those can be, moving like this, they are one of the very, very potential source, thing called as gravitational waves. What is gravitational waves? As you can see from this particular image, you see, the space has some kind of wave structure which is propagating. If things are moving here, itself will start oscillating and you start feeling a vibration back at the end of the room. That means if a galaxy is there, very and this signal is coming from that galaxy, I can possibly see the signal by measuring how the distance between the 2 points are changing. So if the gravitational wave is coming, I will go a little far from you and come back again close, depending upon when the wave is coming or not coming. Is it more or less clear how the signal is going to happen? So, gravitational waves, is it only from particular frequency? The answer is no. It has a wide frequency spectrum, or from very, very small frequencies to very, very high frequencies. You have electromagnetic spectrum, right? Radio, microwave, visible light, X-ray, all of these terms, right? Good. Exactly similarly, there can be gravitational waves of very different frequencies and wavelengths. A nice analogy between both the sectors. So for decades, for centuries, we have seen lights, and now we have started to see something a little different called gravitational waves in some particular frequencies through our detectors. And I will take you there, which has marked the very first discovery of the downward gravitational wave signal with the help of detectors, which is based in US now, LIGO Hanford and LIGO Livingston, which are trying to measure a very, very tiny signal. Do you have any imagination how tiny the signal is? When I said I will move you and I'll come close to you, it is 1 part in 10 raised to 20 is what the signal strength is. So what we are trying to see here is that these are the mirrors which are shooting light of a very, very fixed wavelength. It is coming and reflecting back. And if the space is changing even tiny, the distance between the mirror will change, right? So if I can make a way to measure this very tiny change by measuring the change in the light, I possibly have a way of detecting the signal, which is just 1 part in 10 raised to 20. Just imagine how small this is, the length I am talking about. In very simple way, if I need to get there, I have to control every possible other way by which I can move away from each other. Starting from earthquake to detector noise. And this thing has happened successfully in the technological side to make it possible for the very first detection of gravitational wave exactly 10 years back. For the very first time, we could detect gravitational wave signal in two detectors. This is the property, something is increasing with time, the signal. These are detected at two different detectors of LIGO, and these are their signal, and they match extremely well. This looks like some kind of jitters, right? Some kind of oscillations. Do you agree? Do you believe this is a signal by just seeing it? How many of you believe in it? You believe in it. How many of you don't believe it? You should say yes. And when you see it, you should question, is it really the signal? What is really going on over there? So possibly, let's try to understand what we are exactly seeing on the sky. So this which is a signal increasing with time and gives you some oscillations. So let's try to understand what's happening. So really very far away from Earth, when two particles can move close by, I show you a simple image, now I'm showing a simulation. If these objects are moving like this is the background stars and everything, they will appear like the following. Things are little bit, oscillating, changing. And this is a numerical simulation which tells us when these two black holes are coming close to each other, you can see these green stripes are the gravitational wave signal which is going away. A signal which is bright, dim, bright, dim. So you can see some kind of oscillation in your data. And that's the wave which is propagating throughout the universe before it starts hitting us right over here on Earth. So each of these waves are going on Earth. And Earth is changing a little every time the gravitational wave is going. This is highly accelerated. But to give you the feeling, every time the gravitational wave is going, it is little bit oscillating. And that's the oscillation which you see on that data. Okay? How do you measure it? As I showed you before, these two mirrors starts oscillating together in one detector and in another detector. And when you really combine these lights of extremely perfect frequency, we have a wavelength of about 1064 nanometers. We really start seeing a signal on the detector. If everything is perfect, we should not see a signal. But when there's a little movement because of the shaking of the earth and then shaking of the arms, you start seeing gravitational waves. You start seeing something is moving which shouldn't have moved. Okay? So from the very far away universe, that which has merged right from somewhere on this side of the sky, we are able to see that signal using our detectors in the US called LIGO. Okay? And is it the only thing we have seen so far? Is it the only two black holes we have seen so far? No. We detect black holes in the universe. So from very far away, when you now see those galaxies and those stars in that, think about them maybe having black holes which are moving and gravitational waves may be coming towards you, but we just can't see it. To see it, we need a detector which can see that, such as LIGO. And you can see these are our sources we have seen so far, which are moving and we have detected the similar signal from numerous, many of them. There is also a very special kind of signal we have seen. I have told you about black hole. What about binary neutron stars? One very fascinating signal which we have seen is not only gravitational waves, but also seeing light gravitational waves. And this has happened for a very well-known event called binary neutron star event. It has a particular number called GW170817. It's not very important for you. But what's important is that I told you a particular source can emit gravitational waves. Now, if neutron stars that are coming close nearby, they can also emit light, and that's the light we can see. So now you can see both the signals from a particular source. And this has indeed happened. So on the left hand side, you are seeing a simulation of if two neutron stars are present, the one which we can see on the left, the matter density, or on the right, you are seeing the space-time curvature, or in some sense, gravitational wave density. You see, these two objects are coming nearby, they have a lot of matter, and they emit gravitational waves, and they also throw away all these materials. And together, they emit both light and gravitational waves. And this has been successfully done with the coordination of many telescopes and gravitational wave detectors. And this particular technique has provided us one of the very, very important aspect. I showed you a picture, right, that gravitational wave is propagating through the space and we have detected, right? So how that the universe is expanding? Many of you, right? So how many of you think that when the gravitational wave is propagating from the galaxy, it can have some signature, some imprint of this expansion? Things are going yes, that's right. So things can happen that because the universe is expanding, it will have some signature of the expansion of the universe on gravitational waves. We could measure this. For the very first time, the multi-messenger measurement of the current expansion rate of the universe was performed. And we measured the current expansion rate, what is called as the Hubble constant. And this is our current measurement coming from the gravitational wave data, along with the electromagnetic observations that we have made. So that's so far the story of few sources that I can think about in this talk. So, what is the future of gravitational wave measurements in the next few decades? So, if I tell you how far we see, these are different nearby galaxies and so on. We are improving our detectors. We are seeing much further away in the universe. This is the kind of volume which we would expect to see the currently ongoing detectors. Okay, so our detectors are improving. As a result, I am now can see even far away in the universe than ever before using gravitational waves. And what's fascinating is this particular measurement, because it's extremely weak, you want to make sure you are measuring it using different detectors situated very far away. Okay, we two detectors in the US. There is a detector in Europe called Gorgo, and a detector to be operational in Japan. And this is going to be operational from India and from Maharashtra in the coming few years to a decade. So this has been inaugurated in 2023 by the Prime Minister, and this really started. So this is the map of where the next gravitational detector in India will be made. It is in a place in the Hingoli district of Maharashtra, in a place called Andhra. Moving on, its gravitational science is like India. From very basics of fundamental physics to applications in other areas of astrophysics and applications of several technologies, which you are going to hear from several labs that TIFF today during your entire visit, has immense applications in the building up and operational of LIGO India. I told you in the very beginning of my talk that gravitational signal comes in a spectrum, right? Like everything else. But I told whatever signal I told you, they are all at this very high frequency. So a natural thing to wonder about entire spectrum being left over. Can we detect it? And the answer is yes. One of the very challenging, interesting aspect, which has already opened up, is extremely tiny and gravitational wave signal of nanohertz range. It is almost 9 orders of magnitude less in the frequency than what we have detected so far. What we have seen detectors which has played a major role in that is our very own GMRT, which is in NCRA in Pune. You possibly know about it. So we have seen gravitational using pulsars in the nanohertz range, and with the coming years, we will be seeing even more signal resources using this particular way. At the very, very low frequency, we can detect gravitational wave using cosmic microwave background. And there are upcoming experiments which will be operational in about a decade or so. There is going to be a gravitational wave detector in space, which is called Laser Interferometer Space Antenna, the LISA. And that's going to see gravitational wave in this particular range, which is we call it the millihertz range, or in some sense it is 3 orders of magnitude less in the frequencies than what we are seeing right now. And this extremely high frequency gravitational wave can be seen even better from future gravity detectors. We call it cosmic Experimental Einstein telescope, which are currently in the process of planning. So what you can see that these are detectors which are now we are planning in the future to see the further away universe, and some of you may be taking a major part in that to see the universe using gravitational waves through these detectors. They are going to be operational in 2030, 2036, 2040, and possibly people in this particular future gravitational detectors to discover the universe not only for binary black holes but for neutron stars and possibly very, very early universe signatures. What I will tell you with this in my talk is we are in a very interesting epoch of discovering the cosmos using gravitational waves. And in some sense, there is an entire plan of future detectors which will help us seeing much further and much better. And with this, I will if you want to know more about gravitational waves, that many ways, if you want to know detect gravitational waves, there is a mobile app which you can download and find an alert in your mobile that every time we detect gravitational wave sources. If you want to know more about our research going on at TIFR, please visit our website at TIFR. You will get a lot of details about the kind of research going on in several frontiers in gravitational astronomy. And finally, of course, feel free to contact us through our Gmail account for any questions. With this, I will end my talk. I'm very happy to take any questions from you. Thank you so much.
तो हम अभी 2 क्वेश्चंस ले सकते हैं. किसी के क्वेश्चंस है कोई? You can raise your hands. Okay, yes. You want mic? Okay, yeah.
One question that if we see, we are saying that the gravitational waves do travel toward the Earth, but we don't realize it. They are not that much of, do not hold that much of magnitude. So the detector itself may be very sensitive to it. So my question is on that is, how do we separate the gravitational waves from the other background noise?
Excellent question. Excellent question. So the question is, If we are trying to measure a very, very weak signal, which we don't feel on a regular basis, and our detector can do it, how do we exactly know we can separate other noises? So what scientists are doing is we are trying to build first multiple detectors. We want to build detectors at different locations where noise, optics, behavior of the detectors are completely independent. But when the gravitational wave is passing through this source, they will be always common, right? When gravitational wave is propagating through this through the Earth, all the detectors will be seeing very similar kind of signal. Okay, that's only the first step. The next challenge comes is the extreme control on all possible errors we can make. We need to control the thermal property, the mirrors we have are the finest mirrors ever made on Earth, so that they don't move much unnecessarily. We need to control the earthquake or seismic activities. To the extent, to give you an example, this has really happened that near one of the detectors, once the phone was ringing, and that caused a huge amount of background signal for gravitational wave sources. Some delivery person was calling your phone, and it really caused a lot of trouble for us to make sure that we don't get contaminated by that signal. So the state of the art that we do, you make multiple detectors, you throw away everything that is not common, you find out everything that is common, and you try to regulate or you control your errors at the level of 1 part in 10 raised to 20 to currently see the detection sources we have. And in future, the detectors I showed you, we are expecting our detectors to be better by a factor of typically around 10. Even better by improving our control on the detector noise, so that we can see practically all possible binary black holes in the universe. Answer your question? Thank you. To a very high degree, at the very basic level, yes. So we learned about a very simple concept of Michelson interferometer experiment and applied that on a larger scale to measure gravitational waves. So the very basic physics lab experiments, which many of you are doing, please do it very carefully. So you learn it well to apply it in future to measure something even bigger and much smaller in magnitude. But yes, to answer the question, that is the fundamental unit or concept we use to detect the signal.
Please keep it short, thoda sa. Okay, please keep it short. We are already running late. You can continue, but yeah, we won't take any more questions. Keep it short, please.
Can you hold the mic? Sorry. Sorry, I can't hear you well. Just a minute. Yeah.
Sir, that graph that you help.
Which
Sir,
one? Sorry.
That graph's a signal graph, sir.
Uh-huh.
It's little bit like a black body radiation graph, a emission graph that.
This one?
No, sir, not that one, sir. That signal.
Each of that. This one.
Yeah, this one,
Yes.
sir. This one. It's similar to black body radiation, sir, which.
It's good, very good, excellent. It only look similar in shape, but has nothing to do with it. Neither the x-axis nor the y-axis has anything to do with black body radiation curve. But excellent to see that we could identify the similar shape. It's a very similar shape, but has nothing to do with that particular physics of black body radiation. This is here what you are seeing is the value of the Hubble constant. What is the way to measure the current expansion rate, and this tells me which value is more likely. How much is that? That's the number. Answer question? Okay. No, they are the chair. You have to ask them.
I'm sorry, I cannot take more questions, but you can talk to Dr. Shubhadeep after the talk as well. So please, let's thank Dr. Shubhadeep for a wonderful
Thank you
talk.
very much.
तो अच्छा लगा talk आपको? Can we have lights on, please? And now is the time for quiz. I miss background music, by the way. And ये हम चार आपका क्विज कंडक्ट कराएंगे. And I request volunteers to help us. So क्विज के कुछ बेसिक रूल्स होंगे जो